Day 1 examples. So we got a couple examples to do from the textbook for intermolecular forces. So these are the intermolecular forces examples. And we'll start with 50. And again, this is on the handout in the guided lecture notes. Determine the kinds of intermolecular forces that are present in each of the compounds or elements. Alright, so krypton. Alright, every atom is going to have London dispersion forces. So krypton has dispersion forces. The next question I'm going to ask, is krypton polar? Well, it's an atom, so it's not polar. So therefore, it's not polar. It's not going to have dipole-dipole interactions, and it cannot, by definition, then have hydrogen bonding, because hydrogen bonding is a strong dipole-dipole interaction. NH3Cl, it's going to have dispersion, because it's a molecule. Alright, now, is NCl3 polar? Well, I don't know. You might still need to draw it out. NCl, how many electrons? 26, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Got one lone pair. This is trigonal, pyramidal. So by the definition, it's going to be slightly polar. It will have dipole-dipole in it. Now it's slightly polar because they have the same electronegativity, but it's going to be, we're going to consider it polar for our course. Alright. SiH4. Well, of course, it's going to have dispersion. Is it polar? Well, what's it look like? Si, 4 H's. Alright, we got how many electrons? So silicon has 4. And then we have each hydrogen 1, so 2, 4, 6, 8. This is tetrahedral. And all 4 exterior atoms are the same. They're all nonpolar bonds, so there's no polarity there. That's not the case, so there's just dispersion. Then we got HF, hydrogen fluoride. If it's aqueous, hydrofluoric acid. Of course, it's a molecule, so it has dispersion. And then we have H and F, right? And that's going to be a top 5, right? We got top 5 here. So we have a polar bond, so it's going to be dipole-dipole. And hydrogen bonding occurs when H is bonded to F, O, or N. That's terminal, and that's the case here. And so we also have hydrogen bonding. So that's how we decide what intermolecular forces are present. So let's try 52. Same question. Determine the kinds of intermolecular forces that are present in each element or compound. So all of them now, since it's molecule, 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 and how do I know it's a molecule again? Because it's above the stairs in hydrogen, right? It's all nonmetals and hydrogen. So all these will have dispersion forces. All of them. All of them have dispersion forces. Okay? pH 3. Well, what does this look like? How many electrons? 5 plus 3, 8 electrons, right? P, H, H, H. 2, 4, 6, 8 electrons. It's trigonal, pyramidal. So technically speaking, in our class, this will have dipole-dipole. Now, this is going to be polar. We're going to consider this polar. It's more like, you know, in the terms of scale polarity, it's like going 46 miles an hour in a 45. A lot of people wouldn't even call that speeding. Well, some people wouldn't even call this polar, but based on our definitions, we're going to call it polar. HBr. Right, that's H connected to a top 5. So that's polar bond. So polar bond will have dipole-dipole here. Alright, but no hydrogen bonding. Even though there's a hydrogen bond in the compound, it's not the hydrogen bond intermolecular force. It can get confusing. Right, but the hydrogen force sounds kind of weird. So it's a hydrogen bond, alright, but it's not the hydrogen bond intermolecular force. So bromine is bonded to hydrogen intramolecularly, but not intermolecularly. I know, it's fun. Alright, so that is a polar bond, so it's dipole-dipole. Methanol, CH3OH. We have top 5 here, right? Oxygen's top 5, right? So that's definitely not a symmetrical molecule, so we're definitely going to have dipole-dipole here. But if you notice what's going on right here, H is bonded to a terminal oxygen. So in this case, we can actually have hydrogen bonding. Because H is bonded to a terminal O. I2. I2 is just a molecule, diatomic, I to I. It's symmetrical, there's not polar, and that's it. So that's how we come up with the types of intermolecular forces in the compound. We kind of know what the compound is and kind of how it's bonded. Alright, 56 is the next one. And with 56, explain, or pick the one with the higher boiling point and explain why. So ammonia or methane. So if I look at ammonia and methane, NH3, CH4. Alright, 17.04 grams per mole, right? That's 14.1, yeah. And 12.12. Carbon's 12. 16.05 grams per mole. So there's 1 gram per mole difference. They both have the dispersion forces, or London dispersion, I'm going to call it. I didn't change color. London dispersion. Alright. So London dispersion. Now, methane, tetrahedral, right? Right, it's tetrahedral, and it's not polar. Ammonia is trigonal, pyramidal, and it is dipole-dipole. And since it has H and N bonded with the lone pair, it is also hydrogen bonding. So NH3 has stronger or more intermolecular forces than methane does. So ammonia looks like it should have a higher boiling point and melting point because it has more intermolecular forces over methane. Alright, so that's how I'm going to compare them. CS2 and CO2. So if we look at CS2 and CO2, right, it looks like S and O are in the same column. So SCS, OCO. We're going to have double bonds to both sides. They're both going to be, right, so you look at that, 16 electrons each, right? Alright, they're both linear. They're both not polar. So what's the difference? Well, the only difference is CO2, right, is 16, 16, 32 plus 12, right, is about 44-ish grams per mole. And 32 and 32, it would be 64. So that would be 64 and 12, which is 72 grams per mole. And so CS2 is heavier, right? So I would say CS2 is the answer. And CS2 is heavier or larger. So it has more London dispersion forces. Last but not least, CO2 and NO2. So we look at CO2 again, OCO, 16 electrons. NO2 is 17 electrons, right? We gained an electron, O and O. So now we're at bent versus linear. And so we have dipole-dipole here. Didn't change color on me. Dipole-dipole. Right? So I would say NO2 would have a higher boiling point because it's polar, right? Whereas CO2 is not. And so that's how we're coming up with these explanations. So let's try 53 now. 53, range these compounds in order of increasing boiling point. So the lowest boiling point to the highest. BP, boiling point. Alright, so I'm going to, what are the intermolecular forces? Well, they all have London dispersion, right? They all have London dispersion. So let's look at that. Is any of these polar? Yes. Right? We have dipole, dipole, and dipole-dipole. The last two. Right? Because I have a top 5, and right, they're no longer be symmetrical. If I need to draw these out, go for it. Right? So there's CH4. Right? We got CH3, CH3. Well, HCCH, HH. All tetrahedral. So far, we're all tetrahedral, nonpolar. CH3Cl, H, or CH3CH2Cl, HCl, HH, HH. Boom, boom, boom. And last but not least, so there we go. Drawing them all out. Again, electron count. I do this all the time. I know the electron count. You might have to actually count electrons, right? Carbon has 4. Hydrogen has 1. Chlorine has 7. Oxygen has 6, right? These are the valence electrons. Make sure, right, it goes by that column. Group 1 has 1 valence electron because it's S1. Group 2 has 2 valence electron because it's S2. 13 has 3 valence electron, S2P1. Group 14 has 4, S2P2. 15 has 5, S2P3. 16 has 6, S2P4. 17 has 7, S2P5. And 18 is 8, S2P6. Of course, helium does not have 8 valence electrons. It only has 2 electrons. It's S2. It's 1 S2, so it's done. So it comes from their electron configuration. All right. So, what do we notice? polar and polar, right? We got polar and polar here. So polar, polar. They're also bigger, right? So I have 16.05 grams per mole. I have 12 and 12 is 24, 5, 26, 27, 28, 29, 30. 1, 2, 3, 4, 5, 6, 7, 8, 08 grams per mole. Alright. And these are even going to be larger. Alright. They're going to be even larger. So carbon, of course, is 12.01 grams per mole times 2. Plus, we have 5 times 1.01 plus 35.45 for chlorine. So that's 64.52 grams per mole. And then for ethanol here, I have 12 times 2, 12.01 times 2, plus there's actually 6 hydrogens again, plus 16 for oxygen. And I get 46.08. So there we go. So those are molar masses. Now, there's one more thing here. What do I notice? Hydrogen bonding. Right? Because hydrogen bonding occurs when I have H bonded to F, H bonded to O, H bonded to N. Right? Because there's lone pairs here that this can happen with. Alright? So hydrogen bonding, which is the strongest. So chances are ethanol will have more intermolecular forces than chloroethane, CH3CH2Cl. Now, again, when you go to these, we can make it look like, well, what we can really confuse you, right? Because if I look at I2 versus H2O, that makes sense? Well, we know water is a liquid and I2 is a solid, right? At room temperature. However, water has hydrogen bonding and it's polar and whatnot, and I2 is just London dispersion forces. But I2 has more intermolecular forces than water because it's a solid, right? Well, because I2, right? Iodine weighs 126.9. And there's 2 of them. So that's 253.8 grams per mole versus 18.02 grams per mole. Right? Okay. That's a big difference. It's a huge difference. How do you know it's a huge difference? Well, let's put it this way. Most of us listening to this or watching this can go and put $18 of gas in our gas tank, and there's not going to be major fights or whatnot. We're not going to have to scream at a spouse or a parent or something like that. There's going to be no shouting, man. Like, okay, yeah, you got gas. If we want, some of us, if we go spend $253, $254, might be needed in the conversation, right? It's just not unless it's already in the budget for something, not probably going to be as smooth as $18. All right, so it's a much bigger number. All right, okay, and so our questions are not designed to get you. Like, oh, well, you should have reckoned. Right? We're not there. I just want you to. We're comparing intermolecular forces. So most of these questions that we're going to ask you, in fact, I can't think of one that we're not, is going to, you have the strongest intermolecular forces, it's probably going to be the highest boiling point or highest melting point. And the weakest intermolecular forces, the smallest, will be the lowest. So they're actually written in the correct order. Alright, the lowest should be CH4, and then CH3, CH3, then CH3, CH2Cl, and then CH3, CH2OH. The lowest to the highest. Alright, based on the intermolecular forces. Alright, because they're not 64, 46, not a huge difference. All right. 250 to 18, much bigger difference. All right, so that's how we're going to do that. Don't, so if you like, well, this one weighs more, and not that much. All right, okay, not that much. Yeah, I know it's 46 to 64. It's like 150% more or 50% more, but it's still not. It's going to be in the goal is to make you recognize the types of intermolecular forces and realize that hydrogen bonding polar is stronger intermolecular force than just polar. That's the goal with similar type compounds. All right, so that would be the four examples for day 1.